All right, if you've ever heard the words organic chemistry and immediately felt a little dread, I want you to just forget all that. Seriously, because this isn't some scary class you have to get through. Nope. This is the story of the secret architect that, believe it or not, builds almost everything around you and even inside you. So let's just dive right in. So let's start with a little riddle. What does the soap you use in the shower, the sugar in your coffee, and the gasoline that powers your car, what could they possibly have in common? I mean, they seem totally unrelated, right? But they all share this fundamental chemical secret. And that secret is organic chemistry. The answer is kind of right there in the name. The word organic literally means it's related to life. It's the science that explains the molecules that make us who we are and this whole world of stuff we've made from them. And when I say it's everywhere, I mean it's everywhere. You know, from the second you wake up to the moment you go to bed, your life is just surrounded by these compounds. Think about it for a sec. The clothes on your back, the food you eat, the fuel in your tank, even the medicine in your cabinet, it's all part of the world of organic chemistry. It's honestly hard to find a single moment in your day that isn't touched by it. You know, for the longest time, scientists thought these compounds were just special. They believed they could only be made by living things, that they had some kind of mystical, vital force. But then a chemist went and made one in a lab, and that blew the whole idea out of the water. It proved it wasn't magic. Today, we know the secret isn't a force, it's an element. Organic chemistry is really just the study of carbon compounds. And that brings us to the absolute star of the show, carbon. So what makes this one element so special that it gets its own branch of chemistry named after it? Well, it turns out carbon is the ultimate molecular builder. It's got these two chemical superpowers. First up is tetravalency. Sounds fancy, right? But it just means that every carbon atom has 4 connection points, kind of like 4 universal docking ports. This lets it form 4 really strong, stable bonds all at once. But its second power, this one's the game changer. It's called catenation. This is carbon's incredible talent for linking up with other carbon atoms, forming these long chains and complex rings. They're basically holding hands to build almost anything. And this ability, this tendency to form stable backbones, is the entire foundation for the insane diversity we see in organic molecules. It's the reason we can have millions and millions of different organic compounds, from the super simple to the mind-bogglingly complex. Okay, so if carbon's got these building powers, what's the simplest thing we can make? Well, you just add the simplest element there is, hydrogen. And when you put them together, you get the most fundamental family in all of organic chemistry. So let's meet the hydrocarbons. The name tells you exactly what they are. Hydrogen and carbon, that's it. They're the bedrock, the basic skeletons that almost all other organic molecules are built on. Think of them as the starter pack in our molecular construction kit. Now, they come in 2 main flavors. You've got your saturated hydrocarbons, where all the carbons are linked up with single bonds. They're holding as many hydrogen atoms as they possibly can. Then you've got the unsaturated ones. These have stronger double or even triple bonds between some of the carbons, and that little difference in bonding completely changes how they act. And this is where things get really, really cool. See, a chemical formula tells you what atoms you've got, but it doesn't tell you how they're all connected. So what happens if you take the exact same set of atoms, but just arrange them in a different pattern? Well, you get something called isomerism. Look at these 3 molecules. They all have the exact same chemical formula, 5 carbons, 12 hydrogens. But because they're structured differently, they are completely different compounds with totally different properties. It's just like having the same set of Lego bricks, right? You can build a car, a house, or a spaceship. Same parts, but the results are worlds apart. So you can see the problem, right? With millions of possible compounds, not to mention all these isomers, chemists needed a way to talk about them. They needed a clear, logical system, a language, really, to draw and name these molecules so everyone was on the same page. So, one way to do it is to draw out the full structural formula. It's super clear. You see every single atom and every single bond. But can you imagine trying to draw a molecule with like 100 atoms this way? It would take all day. So chemists obviously needed a shorthand. And that led to this, the condensed formula. It's a really simple way to clean things up. You just group the hydrogen atoms with the carbons they're attached to. It's way faster to write, and for a chemist, it's still perfectly clear what you're talking about. And then, for maximum speed and efficiency, they often just draw the carbon skeleton. In this style, every endpoint and every corner is a carbon atom. You just assume the hydrogens are there, filling in all the empty spots. It's the ultimate minimalist drawing. And the language isn't just about drawing. To avoid complete chaos, chemists developed a universal naming system. You can think of it like a grammar for molecules. There are these clear, logical rules for finding the main part of the molecule and naming all the little branches so that any chemist, anywhere in the world, can hear a name and know exactly what molecule you mean. Okay, so we've got our hydrocarbon skeletons. We can draw them, we can name them, but let's be real, life is way more than just carbon and hydrogen. So how do we get from these simple building blocks to the incredible variety of molecules that actually make up our world? The magic ingredient here is something called a functional group. It's just an atom or a little group of atoms that you can snap onto a hydrocarbon skeleton. You can think of it like a special accessory pack that you click onto a basic tool, and suddenly it has brand new powers and a completely new identity. And this is that power in action. On the left, you've got ethane. It's a simple hydrocarbon gas. But watch this. We swap just one hydrogen atom for that little OH functional group, and boom, suddenly it's ethanol, an alcohol. The properties are completely different. One's a gas, one's a liquid. They behave differently, they react differently. One tiny little change creates an entirely new substance. All right, let's bring this all home. We've seen how this one element, carbon, can form these endless skeletons, and how these tiny little attachments, these functional groups, can give those skeletons a huge range of different identities. It's pretty amazing when you think about it. From the simple, elegant properties of a single element, its ability to form 4 bonds and to link to itself, the entire magnificent complexity of the chemistry of life just emerges. Carbon really is the secret architect of our world. And it really makes you wonder, doesn't it? I mean, if this is what we can get from just one element's unique properties, what other molecular worlds are out there just waiting for us to design and to build?